So for this problem, we need to know what cross-validation is. So first off, let's take this simple example. Just look at the plot on the left. What we have here is a data set of 5 points, and we fit a linear regression. And then we want to know how good our model is performing. So what's our mean squared error? And we can determine that by taking the difference between our prediction, which is the line, and the actuals, which are the points. Calculate that distance. Those are the green lines. And then squaring those values. If we then take the average of all of those squared values, we get our mean squared error of 1.88. Now, the issue is, what if we want to build different models, build multiple models and compare them, right? The issue with 5 observations is the one with the more variables is obviously going to perform better. And it's not necessarily having a better error metric because it's a better model, it's just overfitting to the data. So what we might want to do is build a cross-validated error metric. So that is, ideally what you have is a train validate split, right? We build all of our models on the same train data set, and then there's a totally separate data set that we validate on. So that's the ideal scenario, but obviously when you have 5 observations, we can't really afford to set 2 of them aside for validation. We need all of that data. So a workaround is to say, okay, I'm going to take only 4 data points of those 5, fit my model, whatever that model structure is, and then assess on that holdout data set. So here we're getting our green line for just the first data point when we build our model on those other 4 data points. And then we can repeat that process for each data point. So here we're saying I want to assess my linear model when I only have this x variable for these 5 data points, but just iterate through which observation we leave out. So we have 5 data points. We're going to do that 5 times. And now what we can do is say, okay, I know my squared error for that out of sample observation, and I can square them and then get a cross-validation error, mean squared error, by taking the average of those squared values and getting an estimate of 4.25. So again, when we just fit our linear model, we get a mean squared error of 1.95. If we do 4 at a time and assess on the out of sample and then take the mean squared error, we get 4.25. And since this is a simulated data set, I actually know the true random error noise, and if we square it, we actually get a value of 4. So this cross-validation mean squared error is closer to the true value. And again, that's because it's actually an out of sample estimate of the error. So this is a way we can work around the fact that we want to use all of our data to build our model, but also have a means to assess the model performance without giving an unfair advantage to larger models. So all of this is just to walk through, one, the motivation. Why do we use cross-validation? So that way we get a true estimate of the out-of-sample error. We don't underestimate, which is going to be the tendency if you just use the trained data set. So that is why we're doing this out of sample, and then additionally you can still utilize the full data set to build your model, or most of the data as you build all of these models. The final step is most likely you're going to want to then refit the model on the full data set. We can look at the fact that mean squared error is the summation of the squared errors of our cross-validation model divided by the sample size. So this is for a cross-validation error. In our case, we had 5 observations, so actually that was a special case of cross-validation error, which is called leave one out cross-validation. However, that's not necessarily the case for our problem. So it might be there are 5 folds, but each fold maybe has 10,000 observations. So, we might get 10,000 y-hats from one of the cross-validations and then 10,000 from each of the following. So mathematically, just saying we have each individual observation's error, we can actually say this all works out to be the same thing as taking the mean of the mean squared errors, right? If we were to expand all of that notation, it would work out to be the same thing. So in order to go back to our problem and be able to compare the cross-validation error, they give us most of what we need. All we have to do is calculate the average of those MSEs to get the actual cross-validation error across the entire data set. So all we're doing here is taking those values they gave us to get our cross-validation mean squared errors. So at this point, looking at both of these values, we see that Model 1 has the better error metric. So we know we want to use Model 1, and then it's just the final step of reading the problem. So making sure that you don't get too excited and circle E. It's some number greater than 30,000, so it's definitely E. No, we now need to actually calculate our prediction. So our prediction is our intercept plus, let me see here, I guess we can just scroll up. So we're taking our model coefficients here from Model 1 and then plugging in x values that are provided here. So 500,000, 2,000, and 0.89. We also have our intercept first. So all of that is pretty straightforward, with exception of maybe the intercept, or sorry, not the intercept, the interaction. So when you have an interaction between two numeric terms, all you're going to do is multiply those two values together, and then that product multiplied by their corresponding coefficient. So once we multiply all this out and add it all together, we get a final prediction for Model 1, which is our selected model, of 1,633.8. Scrolling up, we see that falls in the range of C. So that's our final answer. As always, thanks for watching.